Okay. So I'd like to thank everyone for coming to this installment of the Quantum Fluids and Isolation Seminar. So today we have Professor Maxim Metlitski from MIT. Professor Metlitski got his Bachelor of Science in Physics and Mathematics in 2003 and his Master's degree in Physics from 2005 from the University of British Columbia. And he got his PhD in Physics from Harvard in 2011. He did a postdoctoral at the Kavli Institute in Theoretical Physics at the University of California, Santa Barbara from 2011 to 2015. From 2015 to 2017, he had a faculty appointment at the Perimeter Institute for Theoretical Physics. And from 2017 to present, he was assistant professor at Massachusetts Institute of Technology, where he is today. And he's the recipient of many awards and prizes, and most notably 2020 New Horizons in Physics Prize for his incisive contributions to the understanding of topological states of matter and the relationships between them. And today he'll be talking about the boundary criticality of the ON model and D=3 criticality revisited. So please help me in welcoming either by muting yourselves, clapping, or by clapping virtually, Professor Metlitski.
All right, thank you very much, Joshua, for the invitation and the very kind introduction. It's really, it's really nice to have this opportunity to communicate while in isolation. One warning. So I actually gave this talk a couple of weeks ago at the Harvard MIT condensed matter theory seminar. So it will be essentially the same talk. So if you've heard that, I'm afraid you will be rather bored. Right. So I'd like to talk about some recent work that has appeared in this archive preprint, and it's on a very old subject of boundary criticality at the Wilson-Fisher fixed point. But it appears that actually some things about that very old classic problem have been missed. Okay, so let's see. So boundary criticality. So what is this about? Imagine we have a critical system, maybe described by conformal field theory, and you would like to describe, to study the behavior of the system in the presence of a boundary. For instance, you might study the correlation functions of local observables on the boundary, and generally this will have some kind of power law universal behavior with exponents that are actually different from the exponents in the bulk. So that's the first point. Second point is that this boundary behavior, the boundary universality class, is actually not unique. So given a single bulk universality class, there can be different boundary universality classes corresponding to it, and one can tune between those boundary universality classes by tuning some parameters of the Hamiltonian on the boundary. And we'll see examples of that as we go along. So this is actually a really old problem, going back to classical statistical mechanics in the 70s. But recently there has been a resurgence of interest in it, and some of this interest comes from the direction of symmetry-protected topological phases. So symmetry-protected topological phases are of course gapped in the bulk, and they possess some non-trivial surface states on the boundary, potentially gapless surface states on the boundary. Now, a question that has received some attention recently is what happens as you drive this SPT phase through a phase transition, right? So what happens as you close the bulk gap? Kind of the conventional thinking is that the surface states of the SPT are protected in part by the bulk gap. So what if the bulk gap vanishes? Does anything remain of the surface states, of the SPT surface states? And in some cases, it has been shown that the answer is yes. Actually, something remains of the surface state when the bulk gap vanishes. This goes under the name of gapless SPTs. I believe this paper by Tarun Grover and Ashwin Vishwanath might have been one of the first to study this problem, but there's been really a slew of developments on this recently.
Sorry, can I ask a very basic question at the start? Yes, my question is: imagine you put your theory on a torus, and for the points x and y, you chose one point on you choose diametrical points along the radial direction, along the tube, but opposite points. So you would get different correlations if you chose an arc going along the boundary or like through the bulk and then to the other side. Am I clear? Or
are you thinking of what is the manifold that you're thinking about?
Let's say a donut, yeah, the torus.
A solid donut.
Yes.
So
if you pick 2 points on the boundary on, let's say, opposite ends of the cylinder, then you could have correlations completely along the boundary, like so, like in the cube that you've drawn. Or you could also have the correlation penetrating through the bulk and going to the other side.
But the 2 points are on the surface, is that right?
Yes.
Right, so you're asking are you asking like what is the distance? What plays the role of the distance, whether it's like the shortest distance or?
Yes, my question is, if you pick a different notion of distance, you would get different critical exponents, right?
Very good. So here the geometry that I'm imagining is a half infinite geometry, right? So just half of r to the d. Now you could kind of think about surfaces that are non-trivial both topologically and geometrically, and of course that will affect the precise details of these correlation functions. There will be some universal universal scaling functions, which are functions of overall system dimensions and so forth. So
that's clear. That's good. Thanks.
Mm-hmm. Any other questions at this point? So I was talking about this the connection to the SPT physics, and this connection will come back slightly later in my talk. But actually, for most of my talk, I'll be just talking about plain vanilla classical statistical mechanics, no quantum mechanics. And in fact, I will be talking about a very familiar model, which is the ON model. And so it's a classical model in d spatial dimensions. When I say d, I will always mean the bulk dimension. And on the lattice, you can describe it by the following Hamiltonian, which is just you take a d-dimensional hypercubic lattice and you place classical n-component spins on the sides of this lattice, and you couple the sides, the spins with the nearest neighbor interaction, Kij. Now, if you study the system in the presence of a boundary, you can say, okay, if the spins, if the two spins sit right on the boundary, I'm going to set this coupling k equal to k1. Otherwise, I set it equal to k. So you can study the phase diagram of the system as a function of k1 and k. K is the bulk coupling, k1 is the surface coupling. And if you are in dimension greater than 3, again, this is the bulk dimension, then the accepted phase diagram of the system looks like this. All right. So the vertical and horizontal axis, vertical axis is the bulk coupling, and horizontal axis is the ratio of the surface coupling to the bulk coupling. So of course, as you are changing the bulk coupling, you drive the bulk of the system through an ordering transition. You go from a paramagnetic phase at high temperature to an ordered phase at low temperature, and this happens at a critical value k equal to kc, the bulk critical value. So the main question is, what happens to the boundary at k equal to kc? And there are several possibilities. Turns out that if the surface coupling k1 is not too large, then both the surface and the bulk actually order at the same temperature, right? So they order simultaneously. And this is known as the ordinary universality class. However, if you make the surface coupling strong enough, it is possible that the surface orders at a higher temperature than the bulk. So then you have this intermediate phase where the surface is ordered and the bulk is still disordered. As you further decrease the temperature, then the bulk orders in the presence of a boundary that is already ordered. And this is known as the extraordinary boundary universality class. Now, if you sit at kc and you tune k1 over k, then as you go from the ordinary to the extraordinary classes, the transition here is known as the special transition. That's just the nomenclature. Finally, this green line where the surface orders in the presence of a yet disordered bulk, this is just a d-1 dimensional transition in the ON universality class, in the Wilson-Fisher universality class. In order to describe the universal properties of this transition, you can just forget about the bulk, right? Because the bulk has a finite correlation length. You integrate it out, you are left with a d-1 dimensional surface model, and it will have a Wilson-Fisher transition. So this is the accepted phase diagram if the bulk dimension d is greater than 3. Any questions? Now, so far, I've actually assumed that there is no breaking of the ON symmetry of the model either in the bulk or on the boundary. However, it is also possible to turn on symmetry breaking fields. In particular, we can turn on a symmetry breaking field on the surface, right? Just on the surface, not in the bulk. So I call this H1. And you can ask, what is the universality class of the transition then? How does the phase diagram look? And what is thought is that, well, there's actually just one boundary universality class in that case, and this is known as the normal universality class. The nomenclature comes from some fluid statistical mechanics of fluids. Doesn't really matter, but right. So this normal universality class is bulk ordering in the presence of a symmetry breaking field on the boundary. Now, turns out that if the dimension of the system is greater than 3, it is believed that the extraordinary universality class, in the absence of the symmetry breaking field, is actually the same, essentially the same as the normal universality class. This is, that is, morally, it doesn't matter whether you break the symmetry on the boundary explicitly or spontaneously. As long as you have order on the boundary, the onset of bulk order is in the same universality class. This is perhaps easiest to understand for the case of Ising symmetry, where kind of the order parameter is rigid. So this kind of makes a lot of sense. But it's also believed to be true for continuous symmetry, ON symmetry. Essentially, the fluctuations of the Goldstone modes on the boundary of the boundary or the parameter essentially decouple from the bulk if the dimension is greater than 3. They don't play any extra role. So this is a interesting fact. Okay, so far I talked about I talked about the case when dimension is greater than 3, when the bulk dimension is greater than 3. And I think there is kind of no controversy here. The question is, what happens when the dimension is equal to 3? That is, the surface is 2-dimensional. And this will be the subject of my talk. Okay, so first of all, if you have Ising spins, the story in d equal 3 is exactly the same as for d greater than 3. You have the same ordinary, extraordinary, and special transitions. You have a phase where the surface is ordered, bulk is disordered, and the extraordinary universality class is the same as the normal universality class. But things become more interesting when you take n greater than 1, in particular when n is greater or equal than 2. So n, remember, is the number of components of the spin. So let's begin with the case n equal to 2. This is xy spins. So how does the situation change in this case? So remember, we're n equal 2, bulk dimension d equal 3. So what is the new element here? The new element is that above the bulk Tc, the surface cannot have true long-range order. You can at most have quasi-long-range order on the surface. And indeed, if the surface enhancement of the coupling is large enough, then as you lower the temperature, you will first go into a phase with quasi-long-range surface order and finite bulk correlation length. And this transition, the green transition, will be in the Kosterlitz-Thouless universality class. Okay, so the question we want to ask is, what happens at the extraordinary transition here? As you go from the quasi-long-range ordered surface phase through a bulk ordering transition. And turns out that it appears that this question hasn't been settled in the literature, either analytically or numerically. In fact, I found very little discussion of this question in the literature. The only discussion that I found was in this numerical paper by Deng, Blotta, and Nightingale, who have raised the possibility that actually the boundary has true long-range order at this extraordinary line. Right? So you have quasi-long-range order here above the extraordinary line, but then right at the bulk critical temperature, the boundary develops true long-range order. From the point of view of surface order parameter, that would mean that the order parameter experiences a jump from 0 to a finite value as one tunes across the extraordinary line, across the bulk Tc. And okay, and actually in this numerical work, the data, the Monte Carlo data, is roughly consistent with this picture. And this picture seems a little bit strange, and I was looking for ways to shoot it down, but kind of without any detailed arguments, it was difficult to do so. Indeed, while we know that above the bulk Tc, the surface cannot have true long-range order, right at the bulk Tc, kind of all bets are off, right? Because there are critical fluctuations in the bulk. If you think about integrating the bulk out, it effectively induces long-range power law type interactions of the boundary spins. And we know that if we have power law interactions in a two-dimensional system, even with a continuous symmetry, then in principle, Mermin-Wagner theorem doesn't apply. One can have true long-range order, so it's kind of hard to shoot down this picture immediately.
Sorry, can I ask a question?
Yes.
So even the bulk is not ordered, but there are some Goldstone mode or gapless mode fluctuating. There is a possible that such kind of gapless mode in the bulk can also mediate some long-range interaction on the boundary.
Correct, but here we don't have that situation, right? So if we are above bulk Tc, then the bulk has finite correlation length. and so Merman-Wagner theorem applies to the surface. Mm-hmm. Now, once we are on the other side, once we are here, then the bulk is ordered, and if the bulk is ordered, well, the surface is also obviously ordered. One could have kind of more complicated situations where one has a gapless bulk, maybe with some Goldstone mode of one symmetry, and then that Goldstone mode somehow couples to the surface and leads to long-range order on the surface associated with a different symmetry, and that's possible in principle, but that's not the situation here. Does that answer your question, Iji?
Yeah, thanks.
Yeah, good point. All right. So is this actually what's going on? Does one have a jump of the order parameter as one crosses the bulk TC? And the answer is no. So I will present renormalization group arguments that demonstrate that this is not what happens. What one instead finds is that if one looks at the correlation function of spins on the boundary at the extraordinary line, they fall off as a power of the logarithm of the separation along the boundary. And it's a universal power. So the boundary at the extraordinary line is almost ordered, right? You know, the correlation function falls off slower than any power law, but it's not quite ordered. So this goes to 0 as the separation goes to infinity. Another way of thinking about this is you can ask, okay, if I go from above bulk TC, I can ask what is the stiffness, what is the superfluid stiffness of the XY order parameter as I approach the bulk TC, and turns out that it diverges logarithmically with the bulk correlation length, like so. Okay, so this is what I find for the case D equal 3, N equal to XY universality class. And I will refer to this behavior as the extraordinary log universality class, differentiated from the extraordinary universality class that one has in dimension greater than 3, where the boundary is truly ordered at the bulk transition. Okay, now we can ask, okay, that's for n equal 2. What if n is greater than 2? Okay, so here, once we are above the bulk TC, we know that the surface correlation length must be finite, right? Just by Merman-Wagner theorem, there is no, for n greater than 2, there is no either true long-range order or quasi-long-range order. We only have finite correlation length. So from the point of view of topology of the phase diagram, there is no need for a separate extraordinary universality class. It's possible that we only have the ordinary universality class. Okay. Nevertheless, and I think, you know, this was actually the implicit understanding in the literature that if n is greater than 2, one only has the ordinary universality class. But in principle, it's not ruled out that actually part of the phase boundary at bulk TC is in one universality class and part is in another universality class that I will still label extraordinary here for lack of a better name, even though these connect to the same phases above and below TC. You know, this cannot be ruled out other than saying, well, it's not minimal scenario. So actually, which one of these two scenarios occurs? And I will present a normalization group arguments that indicate that actually which one occurs depends on the value of n. So if n is large but finite, one has this situation with only the ordinary universality class. On the other hand, if we treat n as a continuous parameter and make n slightly larger than 2, then we have this situation with separate ordinary and extraordinary universality classes and a special transition between them. And again, the extraordinary class is the at least for n just above 2, the extraordinary class here is extraordinary log with correlation function falling off as a power of logarithm, and this power now depends on n. I will often, in my talk, treat n as a continuous variable. Most interest ultimately is in integer values of n, but it's a useful game to play. Okay, so where does this? So as I said, there are actually kind of pretty rigorous renormalization group arguments in favor of this picture, but there are also kind of more intuitive arguments that one can give. So let me begin with those. So let me begin with the case of n being large but finite. Well, first of all, let's first take n to be strictly infinite and dimension equal to 3. Then, if you just do standard large n calculations, you find that there is no special fixed point when n is equal to infinity. Right? So this fixed point doesn't exist, so likely then one only has the ordinary universality class. Another way to understand this is to approach d equal 3 from above, from d equal 3 plus epsilon. So in fact, whenever d is greater than 3, you can do large n calculations, and you find a phase diagram like this at large n, the same phase diagram that I started with. And furthermore, you can actually calculate universal properties at the various fixed points. And in particular, you can calculate the scaling dimensions at the special fixed point in the 1 over n expansion. And what you find is that the scaling dimension of the order parameter on the boundary at the special fixed point in dimension d equal 3 plus epsilon takes the following form, where I've written this to order 1 over n and to leading order in epsilon. So it looks like as d goes to 3, as epsilon goes to 0, the scaling dimension of the order parameter on the boundary at the special transition goes to 0. What does it mean, scaling dimension goes to 0? Means that one is approaching long-range orders.
Sorry, Max, I have a clarifying question. So I guess you can implement the epsilon expansion differently here. You can have two different epsilons, one for the bulk, one for the boundary. So what's the actual dimension of the boundary in this approach? Is it 2 plus epsilon or 2?
2 plus epsilon.
2 plus epsilon. So you can have a long-range order actually even for n equals 2 or n equals 1 for that matter, right?
You can have long-range order even for large n if epsilon is
even for small n. That's what I'm saying. I mean, you can. It's 2 plus epsilon dimensional surface, so it can order.
It can order even. I mean, usually ordering at small n is not difficult. Ordering at large n is difficult, right?
So sorry. Yes, I reversed. Yeah, you're right. Yeah,
That's correct.
That's what I mean.
That's correct. That's why I have this phase diagram here with d greater than 3, and
but technically speaking, you could have epsilon 1 and epsilon 2 for the bulk and for the boundary. This could be different epsilons.
You're saying so here we are considering codimension 1.
Okay.
Bound,
yep.
But you are right. One could say, one could consider different codimension defect.
Yeah. Right.
That's interesting. I haven't thought very much about that. Yeah.
All right. Yep. Thanks.
Any other questions at this point? All right. So the argument I'm trying to make is that as epsilon goes to 0, the scaling dimension of, at least in this large n approach, it looks like the scaling dimension of the order parameter on the boundary at the special fixed point goes to 0, which really tells you that the special fixed point is approaching the extraordinary fixed point as d goes to 3. These two fixed points approach each other, and then it looks like in d equal 3, they collide and merge and annihilate. So then in d equal 3, one is only left with the ordinary fixed point if n is large. And this is indeed what one confirms with a more detailed renormalization group analysis. Okay, so this is the intuition for why, I don't know if it's intuition, it's some circumstantial evidence that for large but finite n, one only has the ordinary transition in d equal 3. What about for n just above 2? Can we say anything? Well, as I already noted, the way that fixed points appear and disappear is by colliding with each other. Now, in d equal 3 and for n equal to 2, we know what the phase diagram looks like. At Tc, at bulk Tc, there is the ordinary, extraordinary, log, and special fixed points. And all of those fixed points are far from each other. They're not in any sense close. So if I make n slightly larger, then this extraordinary fixed point cannot disappear. So it continues for n slightly larger than 2. And in fact, you'll see that it's of the extraordinary log type. So this is the situation for n slightly above 2. So you see that one actually has quite different behavior as a function of n. And in a few slides, I'll address actually what happens at intermediate n. How does this picture evolve into this picture? But first, let me present a sketch of the renormalization group analysis. This will really be just more the result than the detailed procedure. If people are interested, I'm happy to talk about the details later after the talk. But first, here is a sketch. So let's assume that we are sitting at a large value of surface enhancement, such that there is a very strong local tendency for the boundary to order. And let me describe the order on the boundary by an order parameter n, which is a unit, I normalize it to be a unit vector. And I just consider a nonlinear sigma model for this order parameter on the boundary. For a moment, let me ignore the coupling of the boundary to the bulk. Let me say I only had the boundary described by this action. So two-dimensional system. Of course, in this case, I know exactly what happens. Polyakov taught us how to do renormalization group on this nonlinear sigma model. And if one starts with a small value of g, that is, strong tendency to local order, then this is the RG flow one finds for the coupling constant g. And in fact, g grows as one runs into the IR and eventually blows up. And one interprets this as if you only have a strictly two-dimensional boundary and n is greater than 2, then the boundary, well, if one has a strictly two-dimensional system and n is greater than 2, then the system is disordered. Okay, so this is the situation if there was no coupling to the bulk. Now let's introduce the coupling to the bulk. And I'll just tell you the result of what happens when one does this. Turns out that one can still use the same formalism with the coupling constant g, but the flow equation for g becomes modified due to the bulk fluctuations. The bulk fluctuations alter the coefficient of the g squared term in the flow, and in fact add this extra contribution to it, pi s squared over 2. You see the n minus 2 is the same. I've introduced this minus sign here. This is the new term, which is due to the bulk. What is s? S is a universal constant that depends on n, on the number of components. And in fact, it can be expressed in terms of certain universal amplitudes for the normal universality class. Remember the normal universality class? That's when you have a symmetry breaking field on the boundary. You always have the normal universality class in any dimension. And S is expressed in terms of certain universal amplitudes for that normal universality class. I can explain the details again later. It will not really matter for the main conclusions. But anyway, S is a universal number that depends on N. So what is the physics then? The physics will crucially depend on the sign of this coefficient alpha. If alpha is positive, then G will run to 0 logarithmically in the IR, and this is precisely the extraordinary log fixed point. It turns out that to leading order in G, the anomalous dimension of the surface order parameter is not altered by the bulk. It's still given by this strictly two-dimensional expression here. And if one uses this anomalous dimension combined with this RG flow of the coupling constant, one arrives at this correlation function of the boundary order parameter that decays as a power of logarithm of the separation along the boundary, and the power is expressed in terms of n and alpha. So this is precisely the extraordinary log fixed point that I alluded to in the beginning of my talk. Okay, so this is if alpha is positive. If alpha is negative, then all you can conclude is that the G equals 0 fixed point is unstable in the infrared. Where does the flow run to? We don't know at this point, and I'll say a few words about that in a second. But first let's discuss, is alpha positive or negative? Do we know anything about the sign of alpha? Well, alpha is given by this expression here. So there are actually, we know what alpha is in two limits. First of all, if n is equal to 2, right, xy universality class, then this term coming strictly from 2D fluctuations vanishes. One only has the contribution from the bulk fluctuations, and this contribution is positive. We don't actually know exactly what it's equal to, but we know that it's positive. So when n is equal to 2, alpha is positive, G runs away to 0 logarithmically, we have the extraordinary log fixed point. On the other hand, when n is large but finite, one can use large n expansion to calculate S and to get alpha therefore. And it turns out that when n is large but finite, alpha is actually negative. So this is a calculation that I have performed. So you conclude that as n increases from 2, alpha must change sign at least once. And I'll operate under a minimal assumption that it changes sign just once. Could be more complicated. So let me call the point where alpha changes its sign NC. NC has to be greater than 2 by continuity, right? When n is equal to 2, alpha is positive. So we see that we have this qualitative change of behavior as a function of n occurring at NC. What is the value of NC? I think the real answer is we don't know. If one just takes this large n result and blindly extrapolates down to kind of moderate values of n, one obtains NC equal to 4. There is another calculation one can do that utilizes some bootstrap results that give some of the elements of S, and that gives NC roughly equal to 3. So okay, so this is roughly where NC is. We don't really know. I think that's the real answer. Okay, so what is the, we understand the behavior for n close to 2. We understand the behavior for large n. What happens for intermediate values of n close to NC? Well, we know that at n equal to NC, the leading term in the beta function for G vanishes. And near n equal to NC, one can linearize the coefficient of this leading term, like so, with a greater than 0. So really what happens near n equal to NC will be determined by the sign of the subleading of the next term in the beta function, of the g cubed term. And I parameterize it, its coefficient as b here. So there are two possibilities, be either positive or negative. I'll say right away that we don't know anything about b at this point. To really compute b, it's much more complicated than computing alpha. Okay, so let me consider both situations, both possibilities. First possibility is b is greater than 0. So if b is greater than 0, then what you find is that for n just below nc, there is a perturbatively accessible, unstable fixed point, g star, at which the scaling dimension of the boundary or the parameter is parametrically small. And we identify this unstable fixed point with the special transition. Remember, when n equal to 2, we know that there is the ordinary, the extraordinary log, and the special fixed points. As n approaches nc, those fixed points evolve in some way, exponents evolve, until for n just below nc, the special transition becomes perturbatively accessible in this treatment. Finally, when n is equal to nc, the extraordinary log and the special fixed points collide and annihilate, and for n greater than nc, one is left just only with the ordinary universality class. So this is the picture when b is greater than 0. This is perhaps the most mundane scenario for how things evolve between 2 and n equal 2 and n equal infinity. Questions? However, it's also possible that this coefficient b is negative. Then the situation is different, qualitatively different. As n becomes slightly larger than nc, you find that the extraordinary fixed point shifts from g equals 0, that was the extraordinary log universality class, to a finite, perturbatively accessible value of g here. So this stable fixed point just shifts away from g equals 0. That means that for n just slightly above nc, you have an extraordinary fixed point, but now with correlation functions of the boundary or the parameter that fall off as a true power of separation. Not as a power of log, but as a power of separation. So we call this the extraordinary power universality class, and the exponent will be the exponent of the boundary order parameter will be small for n close to nc. Now we know that for n equal to infinity, there is only the ordinary universality class left. So somehow this extraordinary power fixed point must eventually disappear as n is further increased. So we hypothesize that that there is another critical value of n, nc2, where the extraordinary power and the special fixed points collide and eventually annihilate, and one is left with just the ordinary universality class. So you see that this scenario is slightly more involved than scenario 1, but really one has to be kind of democratic about the sign of b at this point. I don't think we can rule out either scenario. All right, let's see. So which one of these scenarios occurs, and what is the value of nc? Of course, it could be that maybe one has either this scenario and nc is smaller than 3, or one could have this scenario and nc2 could be smaller than 3. Then all the interesting physics is taking place between 2 and 3 at n equal 3, which is like the smallest integer value of n above 2. You already just only have ordinary universality class. That's a possibility. So we don't know at this point, and really we need numerics to settle this. Before I go to numerics, here's another way of looking at the two scenarios. So this is the phase diagram. of the surface as a function of the surface enhancement and n. So in scenario 1, for n smaller than nc, you have the ordinary and the extraordinary log universality classes separated by a special transition. At n greater than nc, you only have the ordinary class left. Dashed lines are just guide to I. In scenario 2, one has, for n smaller than nc, one has the ordinary and the extraordinary log phases with the special transition in between. As n becomes larger than nc but smaller than nc2, the extraordinary log fixed point evolves into the extraordinary power fixed point. And finally, for n greater than nc2, one only has the ordinary universality class. Are these pictures clear? All right. So we don't know which of these pictures holds and what is the value of nc or nc2. So we need numerics to settle that. And there is actually very, surprisingly to me, there is very little numerics on this problem. Really the only numerics for a case of n equal to 3 that I could find for classical Monte Carlo, right? So three-dimensional classical n vector model with n equal 3 are these two papers, not actually very old papers. So let me discuss their results and their interpretations of the results. So first of all, when the surface enhancement kappa is not very large, here the surface enhancement is J1 over J. It is everything, all the numerics agrees. There is the ordinary universality class, exponents, surface exponents can be extracted. Monte Carlo papers agree on those exponents. There is no controversy. The question that is not entirely settled is what happens for moderate to large enhancement of surface coupling. And in this paper by Krech, what was found is that actually if one makes the surface enhancement appreciable, the surface coupling appreciable, then one finds surface exponents that actually depend on the enhancement, that kind of continuously evolve as K1, or here it's called J1, is changed. And this was interpreted as a long crossover to the ordinary universality class for large values of the surface enhancement. So the interpretation in this paper by Krech was that one at n equal 3, was essentially that for n equal 3, one is sitting above either nc or nc2, and one only has the ordinary universality class. However, in this slightly later paper, the authors have looked at something like the Binder ratio for the surface or the parameter. And you see that if you look at this Binder ratio as a function of the surface coupling, for different system sizes, these different curves are different system sizes, you see something like that looks like a crossing point. And this crossing point is suggestive of a special transition at a critical value of the surface enhancement. In fact, one sees a very similar picture if one looks at the Binder ratio for, say, n equal 2 or n equal 1. One sees a very similar crossing point. So if there's a special transition, then there must also be some kind of extraordinary phase here, and the details of this phase are not settled. Whether one has some universal exponents or exponents changing with the surface enhancement, or long range order. This is not settled numerically. So this is all we know from classical Monte Carlo at this point. Questions about that?
Actually, you said that they saw that even for n equals 1, so even in the Ising case, they see this special transition?
The crossing point, right? So the Ising case, I think there is very little there is very little controversy about. The Ising case phase diagram looks like this, right? So Ising.
Oh, right. Okay, yeah, I got you. I just got turned around. Yeah, makes sense.
Other questions? So this is what we know from classical Monte Carlo, but there has actually been more quantum models studied, surprisingly, in the last couple of years, and they've actually been so these are quantum models in 2 spatial dimensions, so 2 + 1 dimension, and there are various kind of geometries that have been studied. But let me actually focus on the model studied in this paper by Weber, Tolden, and Wessel. The other models actually are morally similar, although geometrically a little bit more complicated. Actually, Joshua, how am I doing for time?
Oh, you're fine.
Oh, very good. Right. So here is a prototypical model studied by these authors here. So take a rectangular lattice and place quantum spins on the sides of this lattice, and consider a Hamiltonian that involves nearest neighbor coupling of the spins. Furthermore, let's stagger the nearest neighbor coupling so that it's given by one value on the red bonds and a different value on the black bonds. And generally, we'll make the red bonds stronger than the black bonds. All right. So then you can study the phase diagram as a function of the ratio JD to J. So let's understand what happens in the various limits. If JD is much greater than J, that is, if you make these red bonds very strong, then the spins on the red bonds simply form singlets. Both of these couplings are positive, so antiferromagnetic. Okay, so you lock these spins into singlets, so you just have a trivial paramagnet when JD is large. On the other hand, when JD is equal to J, well, that's the square lattice, Heisenberg antiferromagnet. We know that in 2 dimensions, that has a long-range Néel order. So when JD is equal to J, we have the Néel order. Well, there has to be a phase transition between these ordered and disordered phases. And one finds that this is a phase transition in the classical 3D O3 universality class. This is quite well detailed by Monte Carlo simulations from kind of many years ago. What these recent papers have studied is what happens at the boundary for this model. And here there are actually 2 types of boundaries one can consider. There is what one calls the non-dangling edge, which is this edge composed of spins belonging to the red, the strong dimers, and the dangling edge composed of spins belonging to the weak bonds. And turns out that the boundary critical behavior that one finds depends on whether one is looking at the non-dangling edge or the dangling edge. For the non-dangling edge, one finds boundary exponents that are consistent with the ordinary universality class of the classical O3 three-dimensional model. So no surprises here. This is, as I said, for the ordinary transition in classical models, everyone agrees roughly on what the exponents are, and one finds the same exponents at the non-dangling edge for the quantum models as well. The surprise comes when one studies the dangling edge. And at the dangling edge, one finds boundary exponents, so this is the scaling dimension of the boundary order parameter, boundary Néel order parameter. That's actually very different from this ordinary value. It's, I think you can definitely, in Monte Carlo, on the system sizes, you can probably tell 1 0.2 from 1/4.
So Max, actually, so from experience, I know that such small exponents can be very easily mistaken. I mean, the log could be there actually, in fact, right, instead of a small exponent. So are they sure about this number, or what's the story there?
That's a very good question. Indeed, maybe this is really a log rather than a exponent of 1/4. Nevertheless, as I showed here four different papers, and roughly speaking, all the 4 papers give the same exponent within fairly small error bars, even though that the geometries studied in these 2 papers are quite different. Okay, could be that they're all studying similar system sizes. I don't know. I mean, it's really hard for me to. If it was a log, it would be hard for me to understand why all the papers would arrive at the same small value. Maybe kind.
Mm-hmm. Thanks.
Any other questions? All right. So how to rationalize this behavior at the dangling edge? Well, one thought that people immediately had was, let's consider the case when the spins here are spin 1/2. I didn't tell you so far what spin value is being considered. So let's say that the spins are spin 1/2. Okay, and let's go into this paramagnetic phase here at large JD, right? So then you have, all of these spins on the red bonds are locked into singlets, but at the dangling edge you have a dangling spin 1/2. So then you kind of have a stack of these chains with dangling spin 1/2 at the end. So you can kind of think of this chain then as a kind of Haldane chain with a spin 1/2 degree of freedom at the end. And you can actually think about this two-dimensional system as a weak SPT, which is a stack of Haldane chains with danglings, each one having a dangling spin 1/2. So actually, as long as you have translational symmetry along the boundary, then you know that in this paramagnetic phase, the boundary cannot be trivially gapped. It must either be gapless or it must break translational symmetry spontaneously. So you know that even the paramagnetic phase, the boundary is already non-trivial. If you go very deep into the paramagnetic phase, then actually you know exactly what is the Hamiltonian of this dangling spin 1/2. It's just the Heisenberg chain. You know that it's gapless. Okay, so clearly in the spin 1/2 case, the transition, the boundary universality class of the transition for the dangling edge cannot be the ordinary universality class alone. Indeed, for the ordinary universality class, when we go onto the paramagnetic side of the bulk, the boundary just becomes trivial. But here we know that the boundary cannot become trivial. It must be gapless or break translational symmetry. So for spin 1/2 and the dangling edge, we cannot have the ordinary universality class. So that was people's first reaction. However, the surprising finding was that exponents for people can study this model with any value of this spin, and they did this for spin 1/2 and spin 1, and they found that the exponents are actually quite similar. They're roughly around this 1/4. So this was really surprising. At least to me, this was really surprising, because for spin 1 there is really no need for this dangling edge to differ from the non-dangling edge. Spin 1 chain is gapped, so there is kind of no need for the universality class at the dangling edge to be different. Nevertheless, empirically it seems to be different. So how to explain this? And here is, let me give you kind of a one scenario that maybe can explain this. I'm not claiming that that's what's going on, but just let's entertain this possibility. So first of all, let's discuss what is the difference between spin 1/2 and spin 1 in one-dimensional spin chains. Well, we know how to describe the difference. Haldane taught us. The difference comes from this topological theta term. For integer spin, theta is 0. For half-integer spin, theta is pi. All right. So now let's come back to our classical O3 universality class, boundaries of classical O3 model. And remember, we had two scenarios. We had scenario 1 and scenario 2 for the evolution of the phase diagram with n. So let's assume that scenario 2 takes place, that is b is negative, and let's assume that n equal 3 is slightly above nc, such that for n equal 3 there exists an extraordinary power region in the boundary phase diagram with boundary correlation functions of the order parameter falling off as a power law. And let's actually assume that this 3 is just above nc, such that this exponent, the scaling dimension of the boundary order parameter, is small. And in the simulations at the dangling edge, the exponent is indeed not very large, 1/4. So maybe this 1/4 is actually in the regime of perturbative control. So this is the basic scenario. Now you can say, okay, is this actually for spin that's an integer or spin equal half integer? What is the value of theta? Well, actually it doesn't matter in this analysis. Remember, this kind of beta function is a perturbative beta function derived in an expansion around g equals 0, that is around an ordered boundary state. But this theta term is a topological term, so it actually doesn't contribute to perturbative calculations. So the beta function for theta equals 0 and theta equal pi is actually the same, perturbatively in G, and therefore the scaling dimensions are also perturbatively the same. So this maybe explains the similarity in exponents for spin equal 1/2 and spin 1 seen at a dangling edge in these quantum Monte Carlo simulations. Now you can say, well, actually, are the exponents exactly equal for spin 1/2 and spin 1? What will distinguish the two cases? Well, they will be distinguished by non-perturbative effects associated with this topological term. Classically, such configurations are skyrmions that have a classical action given by this expression. So if we just naively replace the coupling constant G in this classical action by the fixed point value, right? There is a fixed point. Then, re-expressing it in terms of the scaling dimension on the boundary, this is the suppression of the skyrmion configurations that one obtains. So this looks like a rather large suppression. So maybe that's what explains the similarity in exponents for spin equal 1/2 and spin equal 1. Strictly speaking, they will be different exponents, but numerically they could be very close. All right. Here is another comment. So far, I focused mostly on the physics associated with the Néel order parameter, with the magnetic order parameter on the boundary. There is another important operator on the boundary, which is the valence bond solid order parameter. Right? We know that valence bond solid order parameter is very important in one-dimensional spin chains. Well, what is it? It is just the dimer correlation functions at momentum pi. So I call this valence bond solid order parameter V of x. And well, in a one-dimensional spin chain, in this nonlinear sigma model description, the quantum numbers of the VBS or the parameter are the same as those of the Skerman density. You can convince yourself of that. So we identify the two. And now we can ask, okay, in our scenario, what is the scaling dimension of this valence bond solid order parameter? Well, it's the same as the scaling dimension of the Skerman density, but perturbatively, the scaling dimension of the Skerman density is 2, right? Because we know that perturbatively the theta angle does not run. If the theta angle ran, then we would run into problems with periodicity of theta. So perturbatively in G, theta does not run, so Skerman density has dimension 2. So that's the prediction, that the up to non-perturbative effects, the same non-perturbative effects as I've discussed here, the scaling dimension of the VBS or the parameter at the dangling edge should be equal to 2. So maybe people can check this fact numerically. All right, so that's the scenario we are invoking to explain the quantum Monte Carlo data. That is, there is this extraordinary power region, both for integer spin models and half-integer spin models. Now you can ask kind of question about broader phase diagram, right? Let's say we take this dangling edge and we start modifying the Hamiltonian on the dangling edge. Can we eventually drive it into a regime where we have the ordinary universality class? Well, for integer spin, the answer is yes, and you know, we can have an ordinary universality class, and then the special transition between the extraordinary power and the ordinary universality class will just be described by, well, whatever the special transition in the classical model here. For the half-integer spin, for s equal 1/2, we cannot have the ordinary universality class at the dangling edge by itself, as I already said, right? Because if you go on the paramagnetic side, the boundary must be non-trivial. So we guess that the ordinary universality class must be actually accompanied by a spontaneous breaking of translational symmetry on the boundary and the boundary VBS order. So we can imagine that actually for the case theta equal to pi, that is for half-integer spin, this special transition is really a transition between the extraordinary power universality class on the boundary and the ordinary plus VBS universality class. So this is, this is an interesting kind of deconfined critical point where, well, you have onset of valence bond solid order and something is changing about the correlator of the nail order parameter as well. And actually a theory of such a continuous phase transition has been, such a continuous boundary phase transition has been presented in a paper by Xiaomin Zhang and Chenke Xu. So that's kind of a different viewpoint onto the problem that starts not from the region of large surface enhancement, but kind of rather works around this point, this special transition. It's still not entirely clear whether such a direct transition is possible, but maybe it's possible. So let me probably conclude now by saying that, we found surprises in the boundary critical behavior of the ON model when the bulk has dimension d equal 3. Something non-trivial has to happen as n evolves from 2 to infinity. We describe these two scenarios for the evolution. We don't know which one occurs, and I hope that this will be settled by Monte Carlo, both classical and quantum. I think it's very surprising that in 2020 we still don't know what is the critical behavior, boundary critical behavior of the O3, classical O3 model. Right. One remark that I didn't have time to describe this, but actually, so for the quantum models, I've mostly focused on the case n equal to 3. There is something interesting that also happens for n equal to 2 for quantum models. That is, for n equal to 2, that's like XY universality class, or you can think of superfluid to mod transition. And then one parameter for the boundary universality there is actually the filling of the boundary. The filling on the boundary compared to the bulk filling, filling being the density, can be incommensurate or can be some fraction. And turns out that when the filling is incommensurate, one actually can describe not only this extraordinary log universality class, but also the special transition. It's a kind of a KT type, but not exactly KT. Right. So let me stop here, and thank you.
Okay, so now people can ask questions. If you have a question, you can either raise your hand or you can just unmute yourself if you like.
Max, thanks for a very detailed and interesting talk. I mean, what's holding back future classical Monte Carlo results here? Just somebody doing it? I mean, it seems like a totally trivial thing to do. Just throw a classical n spin on a hypercubic lattice and let it go. I mean, just big system sizes. I mean, we have GPU algorithms to do these, to do huge system sizes. All kinds of stuff is known.
Yeah, I don't understand what's holding back. I think system sizes that have been studied here for these classical Monte Carlo simulations are, they're not tiny, but they're not state of the art. Okay, I don't. Okay, so you see that it's actually here is L equal 100. So I think they go up to like 64 in each direction. Okay, these are not tiny systems, but I don't think these are kind of state of the art. That would be possible now. Please correct me if I'm.
You should be able to do much larger than that.
And another point that I'd like to make is that it's, I haven't worked this through carefully, but it's likely that you can reformulate these, classical models as loop models. Mm-hmm. And there the parameter n can be made actually into a continuous parameter. So not only might you be able to study n equal 3, but you might be actually able to study the entire evolution. Which would be also very interesting.
Yeah. Cool. Thank you.
Any other questions? And the system sizes studied in quantum Monte Carlo are also similar. I don't think I have a plot here, but I think there are about 50 spins along the boundary.
Any other questions? So maybe I'll wait about 4 seconds in case anyone wants to unmute themselves. Okay, so let's thank Professor Metlitski again.
Thank you.
Thank you for coming.
Thanks, Max. And thanks, Josh, for continuing to organize this.
Thank you, Professor Maestra.